طيب بسم الله الرحمن الرحيم. So we talked last time about the Aloha, the unslotted Aloha and slotted Aloha as well. So today we need to drive quickly the efficiency for the slotted Aloha first, because the slotted Aloha is easier to drive. And then later on we'll talk about the difference when we consider the unslotted Aloha. So for slotted Aloha, we know that we have a synchronized transmission. So we have only one slot. So a node cannot send in the middle of the time slot. So we know that for sure. So the efficiency is based on many infinite nodes trying to send on the channel, and what is the maximum throughput that we can get using all this infinite number of nodes. Okay? So in order to do this, we can try to make certain assumptions that we will assume that a node is trying to access the channel with a probability P, where P is just a random variable, or a probability that can take any value from 0 to 1. We don't know when the node is going to send on any time slot, but we know that the node will access this time slot with a probability P, and which means that it will not access this time slot with a probability 1 minus P. Okay? So what is the probability? So the probability that any node sends successfully equals the probability that this node will send on this time slot, right? Which is a P. Okay? And all the other nodes will not send on this particular time slot. What is the probability that all the other nodes will not send on this particular time slot? 1 minus P. Okay? So if we have n nodes, okay? So n minus 1 nodes will have to abstain from transmission, will have to not access this time slot, which means that the probability is 1 minus P to the power n minus 1. So this means that one node will send with a probability P, and all the other nodes. When we say and, this means that we multiply the probabilities, right? So, like for example, node 0 will send. Node 1 will not send 1 minus P. Node 2 will not send 1 minus P. Node 3 will not send. And then when we say and, multiply all the probabilities together. Okay? So any node I, this is for any node I. Okay? If we want to if we want to calculate the probability of success given all the nodes send successfully, this means that either node 1 will send successfully, or node 2 will send successfully, or node 3 will send successfully, or node n will send successfully. The probability of each of them is this. Okay? Then the probability of all of them OR together is what? When we say OR in probabilities, this means that it's addition. Okay? So this means that the probability of any of the n nodes sent successfully is a
n into p n into p into p 1 minus p over
n. We multiply by n here.
Yeah, multiply.
Right? because it's the probability of first node sent successfully, second node sent successfully, and n nodes sent successfully. So this is the probability that all the n nodes will send successfully. Okay, so so what is the maximum? What is the maximum of this probability? What is the maximum of this probability?
N.
N? How?
What was the question? What is the probability of?
What is the maximum? What is the maximum?
The maximum P is 1. So 1 times n. Right.
Wrong.
Because it's 1
Let's-
minus P. So okay.
If,
it should be,
if you know
it's
the
one,
probability,
so it's
if the probability is 1, then
1 minus 1 is
Zero.
0 and then yeah. So
Type.
0
0.
should be. Okay, no. So
If P is
probability of
0,
0
then what is this?
If P is 0,
If P
then
is
it is 0.
Is 0.
yeah,
So neither 0 nor 1 will give me the maximum for sure. So it should be somewhere in
Between.
between. How would we know this? This is a function of P. How can we get the maximum?
the maximum of
The maximum of this function. How can we get a maximum of any function now?
is
What?
it degree?
How can we get the maximum of any function? Any polynomial function. How can we know the maximum value of? Huh?
Differentiating.
أيوة. Why are you shy saying it? This is perfect. This is correct. So we need to get the derivative of this function with respect to p.
Right. That's it.
Right. So if this is the probability, then we differentiate this probability with respect to p. So what is the differentiation of this? So the differentiation of f, assuming that this p, this probability is f, okay? So we get the derivative of this f with respect to p, and then we set the right hand side with 0, right? So what is the derivative of this
With respect to P.
with respect to p? Okay, so the derivative of this is basically the derivative of this multiplied by this, and this multiplied by the derivative of this. These are two functions which are multiplied together. What is the derivative? What is the derivative of this? It's n, right?
Yeah.
Derivative of np is n,
Right.
right? Multiplied by this, which is 1 minus p, n minus 1,
Okay.
Okay.
The,
plus
the other side.
the np, and then the derivative of this. The derivative of this with respect to p is what? Is n minus 1, okay, multiplied by 1 minus p, n minus 2, and then multiplied by the derivative of the one inside,
Yes.
which is minus 1. So this will be minus, right? And then we set everything with 0, right? Of course, n would be gone, right? And of course, we can divide by 1 minus p to the power n minus 1, because it's common.
Right.
So this means that we will be left by 1 minus p here,
Equal.
minus p n minus 1, okay, بتساوي
0. Stop.
that's it, right? Okay,
Right.
all right, so this is 1 minus p minus
Minus
np
P,
plus 1.
لا بلس P. صح بلس P. So دي بتروح مع ال V.
لا لا minus p times n.
minus b minus nb بعدين plus b.
Sorry.
We multiplied b by 1 صح؟ b times minus 1.
Here, sorry, 1 minus p here, n is gone, and then 1 minus p minus p times n minus 1, and this is gone. So this is gone, and this will be 1,
1.
right? So it's 1 minus p minus p times n minus 1. صح كده؟ minus plus p here. Right.
b بتروح مع b.
Right. Yes.
Minus NP
So
Equals
it's
0. So p will go, and then
1 minus np.
1 minus np, which means that p equals a.
1 over n.
Okay. So this means that the probability that will maximize this is neither 0 nor 1.
It's 1
It's
over.
actually 1 over n, which means that all of them will have to access the channel with a probability that's close to 1 divided by the number of nodes. Okay. So what is f when p equals 1 over n? Of course, n divided by n is. So this will be 1 minus 1 divided by n minus 1.
What is that?
So I actually substituted this in this because I know that p equals 1 over n to maximize this probability. Okay. Okay. So when p equals 1 over n, this is the value because n divided by n is 1, and 1 minus 1 divided by n. So this is the maximum probability. Okay.
Of all the nodes sent successfully. Of all the nodes sent.
Right, and this is like the best. This is like the best when all of them send with a probability which is equal 1 over n. Okay. The only thing left here is to take the limit of this when n goes to infinity, which is trying to reach the maximum value. Okay, when n is really high. Okay, and it turns out that in fact this is 1 divided by e. Remember e here اللي هي e اللي هي 2.3 something, which means that the maximum efficiency I can reach is around 35 or 36%. اللي هي 1 over e. So 1 over e here is because e is 2.3 something or 2.4 1 مش عارف يعني ما اعرفش الفاليو بتاعتها. So this is actually 1 over e is around 37.37, which means that the efficiency is 36%. What does that mean? This means that if infinite number of nodes trying to send with a huge load, what will get through eventually is 37% of this load will get through successfully. The rest will be gone. This is the max, assuming again that we have a huge amount of nodes trying to access the channel. So if we get this function as if we try to actually get the relationship, as we said before, if the number of nodes are trying to access the channel with very low load, what will happen is that the collision probability will be minimal, almost none. So we will see that if this is a function of the load, where the load is actually p. يعني if p is very small, this means that what we will get, and this is the throughput, okay? What we will get is actually, we'll start with 0, of course. If P is 0 or if the load is 0, then we'll get 0. But then when we increase a little bit, we will start to see some linear trend, which means that the probability of having collision is very low, right? Which means that all what we are trying to send will get through. But that's when the load is very small, okay? So what will happen? We'll keep increasing, but we will see somewhere that we will start to get collision, in which case we will go from a linear perspective to a logarithmic kind of behavior. So we'll see that we are increasing the load, but what we are getting through is less. Until we hit a maximum period, that's when P equals 1 over N, okay? Okay? At this point, exactly, at this point, the throughput starts to decrease. Why? Because the collision will be dominating. Collision will dominate in this case. Will start hitting or dropping the throughput of the entire system lower. Right? And then this will start to decrease exponentially depending on, so if we rely on P only, then we'll stop at P equals 1, in which case when P equals 1 you will start to find that it's 0 here. If we base the load based on P and N, so in that case it's a function of when the N also increases. So if we fix P to something higher than 1 over N, and we keep increasing N, then in infinity you will also reach 0. Okay, because when N is infinity, 1 over N is also 0, which means that also the throughput will be 0. Okay?
It means if you increase the number of nodes,
you increase the load, and if you increase P, you also increase the load, because the load is actually function of both. The actual load is function of both. It's function of how persistent you are in accessing the channel at every time slot, and also how many nodes are trying to access the channel at this time slot, right? So both of them we will calculate or will estimate the amount of load on the network. Okay. So as we can see, the load, when the load increases at the beginning, and this is why that here in Doha we were quite fine, 10 years back with the roundabouts, because the roundabouts were really nice. No one is stopping. The load is really low. Okay, so the throughput is very good. No one is expected to wait. You go into you don't stop at the stop sign. You just you go right, across the sometimes without even checking anything. So you go straight. But then when we started to get the load higher and higher, we started to get more and more accidents. That's when we started to feel like, no, it's serious and we need to change the roundabout. So now we have to change, even though the traffic signs, they introduce overhead. This overhead is equivalent to carrier sense multiple access with collision avoidance, something like that. It's like before you access, just look, and also try to avoid by waiting for a certain time to make sure that nobody else is accessing before you get into the intersection. So you use some precautions before you, so that reduces the throughput a little bit, but in fact it increases the efficiency overall because it tries to reduce the collision. Okay, so if this, when we talk about these types of medium access control, you will see that it actually goes higher. it actually goes higher. Okay, even when the load is high, the throughput increases. Why? Because with this amount of precautions that we do, we reduce the collision. We do not eliminate it, but we reduce it. When we reduce it, the throughput gets increased. But we feel this only when when the load starts to increase. When the load is reduced, actually Aloha is perfect. Aloha is perfect. No one beats Aloha because it has no overhead. Okay. Clear?
Y-axis is efficiency, no?
Y-axis is the throughput. Throughput is the successful transmission. The transmission that gets through.
So, doctor, this happened when the probability is fixed and the number of nodes is increasing.
Yes, then it will reach zero only in the infinity. In infinity. Okay. All right. So that's for the slotted Aloha. For the unslotted Aloha, the problem with that is that we do not have boundaries. Right? So a node can send at any point in time, which means that if we have a node, node I is trying to send a frame, so what is the probability of success in this case? Well, if the node is trying to send at time t0, the frame itself takes one time slot, right? So if a node sends in any time before it, which is from time t0 until from time t0 minus 1 to time t0, if a node tries to send in any of these in this time slot, remember it's free. The nodes can send at any point in time, right? This will overlap with this, which means that collision, right? This same node, this exact same node, may select to send here, which is mainly in this time slot, and this will also collide, right? So a node, one node, may actually collide with node I twice, right? The same node may collide with node I twice because it tries to send here and then it finishes and then it will try to send here as well, right? Which means that what is the probability of success in this case? What is the probability that node I sends successfully? Equals node I will send and all the other nodes, they will not send at this time. And also all the other nodes will not send at this time. Right? Because the same node may actually interfere with this node twice. One before it and one after it. So if any node tries to send before that frame, the collision may happen. If any node tries to send after it, also a collision may happen. Because any overlap for us is a collision. So that's the only difference. So,
but maybe we'll multiply the whole thing with time, something related to time. So?
No. That's it. No, it's statistical. Statistical does not have time.
Okay.
So 1 minus p to the power 2n minus 1. So the probability of success here has been reduced. Has been reduced. Why? Because of lack of control here. Because any node is this is the complete freedom. And that's why complete freedom is not always good. Right?
Overlap occurs, collision occurs, it is discarded.
Yes, of course, it's discarded. So the probability of success due to lack of synchronization in the unslotted Aloha is lower. So this same thing, we do the exact same procedure, okay? And we calculate for P, which maximizes this, the exact same thing that we have done before, okay? And we calculate when n goes to infinity. So in fact, in that case, we will find that the efficiency, because of this 2n minus 1, will be 1 over 2e, which is half what we had before. Okay? The exact same curve that we have done is valid here, but the maximum is reduced from 37 or 36 to 18% only, which is really low. Really, really low. So this is an indication that ultimate freedom is not good. Okay? So people have to have some they have to have some alert, some sense. Okay? So if we do this only by time slots, we can increase this efficiency to double. Okay? But of course, even 36% is not enough for us. So we need to reach higher efficiency, in which case we can use more levels of precaution, like carrier sense multiple access. We can add collision avoidance, because in wireless we cannot have collision detection. We can have collision avoidance, right? So when we add collision avoidance on top of this, and as we will see later, we can use RTS, CTS. If you remember RTS and CTS, this is another level of precaution. So when we add all these precautions, we can push the efficiency a little bit high, hopefully to the 90% level or even higher if we can. Okay, so that's what we will try to do. We know that Aloha is very good, but in low system loads. So because of the fact that this efficiency is low, what we could do is to try to perform some reservation. And reservation here we mean that with the slotted Aloha we were able to increase the efficiency, but we need more than that. And one possibility is to use reservation, which means that we try to reserve the channel for a period of time for a particular node. When we try to do this, all the nodes will know that this node is reserved or assigned to this particular duration, in which case all the other nodes will refrain from transmission. Okay? But as we will see, this reservation itself is an overhead, and it requires some mechanism how to perform that reservation. Okay?
After even in very low system loads, the maximum efficiency is 37%. No? Even if the load is very low for Aloha.
The efficiency, the maximum efficiency is defined as the infinite number of nodes trying to access the channel at the same time. Then we can get to the maximum efficiency. The efficiency that you are referring to, if the efficiency is the rate of successful transmission divided by the load, then in low loads, the efficiency is 100%. Right? The low loads is 100%, which means that the amount of transmission that we get successfully is actually the same transmitted data. Okay, so this will be almost valid, but after some time you will find that you will start to encounter some collision. When you encounter some collision, this collision will increase as the load increases, which will drive the efficiency below 100%. This is the difference between Aloha and any other protocol. Aloha can, in fact, in very low loads, can get to almost 100%, like 99.9. Can get to almost 100%. All the other techniques, they cannot get as high as Aloha in very low loads. Okay? But in high loads, these techniques, they get to higher throughput, much higher than Aloha. So in order to avoid this low efficiency, we can use reservation. By reservation, we mean that we will reserve the channel in the future to a particular node. This reservation can increase the efficiency up to maybe like 80%, and in some cases even higher than that. Because sending within the reserved time slot is collision free. So once we reserve the time a specific duration, then only one node will send during the reserved time slot, which means that it's collision free. However, in order to facilitate this reservation, okay, we need to have the period of reservation itself, which is what we will talk about. So Tdma, if Tdma is collision free, but it fixes the time slots. So the reservation is fixed. However, here, because the reservation itself is dynamic and it changes over time, so we need a reservation phase, okay, which we have to agree about how the durations are reserved for the nodes in the next duration of time.
I can't find the network connection.
Okay, so from time to time, we can change the reservation for the different nodes. So we will see how this is performed. So many techniques, like in satellite links, they use this reservation. However, even reservation, as I said, requires some overhead. Okay, so there are three different ways of performing reservation. One is explicit reservation. One is implicit reservation. In implicit reservation, we do not have a separate phase called reservation, and we will see how this is done. Or reservation Tdma, and we'll see also how this is done. Okay. So the first explicit reservation, or what we call dynamically assigned slots, in that case, we have two phases. There is a reservation phase, okay, and then there is transmission phase. So each frame, each big frame, is divided into two phases. The first phase is the reservation phase, and the second phase is the transmission phase. In the reservation phase, we do not have what nodes are accessing which time slot. So in this phase, they use slotted Aloha, but not for sending transmission, for sending a request to access this time slot. So during this phase, we will divide this phase into many small time slots. In every time slot, the nodes will contend on accessing this time slot using Aloha, slotted Aloha in that case. Okay? Which means that if a node sends on this time slot successfully, this means that this node will have this time slot reserved for it, which is the first transmission time slot. If a node tries to access the second time slot, it's the second mini time slot, and the transmission is successful, then it will access this time slot exclusively, and nobody else will access it. If two nodes contend on one time slot and they collide, this means that
They won't be able to get.
they won't be able to access the time slot, this transmission node. So that's why usually when they send the request goes to a centralized coordinator, which is like an access point. And the access point will receive all these requests. And based on that, it accommodates or endorses this request. Okay? So it endorses this request. Okay? So in the explicit reservation, you have two modes. There is Aloha mode for reservation, and Aloha here we mean slotted Aloha for reservation. And then competition for small reservation slots. In that case, collision is possible. If two requests collide, then those two requests are gone. They will not access anything. And then all these requests will go to a specific node, which will then endorse this request by assigning a specific time slot during the transmission phase. Okay?
For
So
time slots, two time slots for each node. Like
no, well, it depends. Maybe a node will send a request to request two times slot. Again, from here to here, there are multiple variations. A node may send a request to request a specific time slot. Okay? In that case, the access point will either accept or reject. Okay? They accept or reject. And in all cases, it accepts. خلاص, that's it. But in that case, when the node sends the request, the node should try to select a time slot that's different from all the other nodes. Okay? In that case, they use what we call random dynamic reservation, which means that every node will send in its request the exact number of the time slot that it wants to access by generating a random number from 1 to p, where p is the number of available slots. Okay?
So B is the random number here?
P is a random number, but in that case, it's not probability. The random number here is from 1 to the available number of slots. So assuming the three of us are now trying to access these three channels, each of us will generate a random number. So
What if it was more than what I need?
collision. خلاص. If A?
If I propose a P which is more than what my need. If I said
No.
10,
The index of the time slot, not the number of time slots. يعني the three of us, each one will generate a random number.
Okay.
So hopefully, the best case scenario, you will generate 1, she will generate 2, I will generate 3.
Okay.
In that case, each of us will send the request again in the reservation phase, and hopefully when we send it, we will not collide together. In which case, we will send in three different Aloha time slots. In which case, all our requests will go to the access point. The access point will receive all the three requests. The access point will say, okay, 1, 2, 3, fine, okay, you will access 1, you will access 2, I will access 3. So it will accept all of them, that's it. There is a probability that two of us will generate the same. Yeah, hopefully when we generate a random number, hopefully the probability of collision in that case will be very low. But it's not 0. In which case, this time slot, we will have collision. So this is what we call dynamically selected reservation.
but this access point is allotting particular time slots to each of us.
Right.
So how,
But in this particular scenario that we're talking about, we select which one to send, not the access point. Because what might happen as a different technique يعني. Our requests will not contain the exact time slot that we want because we don't have the global picture, right? But what we could do is that to request, I want 1 or 2 time slots or 3 time slots depending on what I want, and then all our requests will go to the access point, and then the access point will have to send to everyone what it has for each one. Maybe you will send your request with like 3 time slots. I don't have 3 time slots for you. Depending on the requests that I received as an access point, I can give you only one. And give you only one. Then I send one frame to all nodes. You will have time slot 0 only. You will have time slot 1, and I will have time slot 2. Whether this was what you have requested or not, maybe you have requested more than that, but the access point does not have resources for all of us. Okay? In that case, who made the decision? Not us, the access point. In the first scenario, who made the actual reservation? Us, by just random. Okay? So what I mean is that from here to here, there are multiple possible variations. We can select which time slot that we want by the nodes themselves using random number. The good thing about that is that the engagement of the access point is minimum. So it either accepts or rejects, that's it. And in many cases it accepts. But the access point does not have to perform any intelligence
To check if they're the same or not.
to check if they are the same or not, to check what you want, what I want. It doesn't have to do all of this, right? The other variation of this is that when the access point receives all the requests, and then it has to perform some intelligence to know that in your request you have said that you need 2. In your request you have said you need 2. In my request I need 1. Okay, I have only 4 time slots. So which one do I give 1? Which one do I give 2? Okay. So it looks at the quality of service of each node and it performs certain procedure, and then later on it says, okay, so based on my calculations, you can get 1, you can get 2, I can get 1. So here at the end of this, it has to send a frame to all of us to inform all of us who will access which time slot. Okay? Explicit reservation here refers to this, the fact that we explicitly send our requests to the access point. That's why it's called explicit reservation. Okay? But the actual mechanism for reservation can take several variations. Whether in our request we can explicitly request the access for a particular time slot, or we send the fact that we need 1 or 2 or 3 time slots, and then we leave it up to the access point. Okay? So if we are in the first scenario and a node wants 2 time slots, then it has to send 2 requests, and it has to generate random number for 2 time slots if it wants. Okay?
Only if the random number
is different. Collide, yeah, which is very low probability.
So how does this collision happens here?
Here?
Only the Aloha, right?
In that case, we could have collision here or here.
Also on the reservation, if it's accept both in the same.
Yes, if we have 2 reservations, okay, they did not collide, but based on randomly generated number, you have generated time slot 2 and you have generated time slot 2.
But
So
it
it
should
happens.
be detected in the Aloha mode, right?
No,
The
because
follow-
the requests are sent at 2 different time slots, but the requests contain a request to access the same time slot in the transmission
And
phase.
it's not intelligent enough in order to.
So
detect it,
yes,
so-
in that
okay.
case, the access point will say there is no access point in that. I don't need any access point in that case because the access point does not have to control anything. Okay.
Only in that case this collision happens.
Yes.
If the access point is allotting us time slots, then no collision happens.
No
Because
collision
it
happens.
differs.
Yes, but it requires always that you need to have a centralized controller. The good thing about explicit reservation with with randomly generated requests is the fact that you don't need to have an access point, because you request the access to a particular time slot based on a random number. Okay? So in that case, we don't need the access point. They usually use this for satellite communication, because in satellite communication, to rely on the satellite to control the access to the channel will encounter very, very high delays. Because if you rely on the fact that you will send your request to the satellite, and then the satellite will send back some approval or endorsement to your transmission in order for you to send your transmission, then you will have to wait for a very, very long period of time, because the uplink channel and the downlink channel has very large delays. So instead, we don't need to rely on the satellite to endorse. So in that case, we will request the access to a particular time slot, okay, randomly, by generating a random number. So hopefully, these random numbers will be different. So the probability that we will request the same time slot is very low. But when that happens, collision will happen. But this will be much better and much more efficient than waiting for, the satellite to send you back and forth some control signals in order to provide the transmission. Okay?
This is used in all communication systems, so not really satellite, but for all everything.
Well, the concept itself can be used in different communication systems. However, the explicit reservation using the randomly generated time slots, okay, is used by the satellite communication. Okay, but explicit reservation is just a concept. Here we're just explaining some concepts. Okay. All right. So there is another way of reservation, which is what we call implicit reservation. In implicit reservation, or what we call packet reservation multiple access. In packet reservation multiple access, we do not have a separate reservation phase. We do not have that. Okay, so we divide the frame into slots. We divide the transmission frame into slots. Okay, so here we require an access point in that case, and I will tell you why. We will divide the frame into time slots initially, and then in each time slot, the nodes will contend on this time slot, which means the node will contend, which means that we will try to access this time slot successfully by sending data. Okay? If this data gets through, the access point after the end of this frame will announce the fact that node A was able to get this time slot successfully. What does that mean? This means that node A has seized the access to this time slot forever until there is a time slot that's assigned to A becomes empty, which means that node A does not have data to send, more data to send at this time slot. In which case, this time slot will be announced or labeled as available. So all the time slots that are available for all the nodes to contend to gain access to that time slot. Okay? So at the beginning of the system, all these frames will be labeled as available time slots, which means that any node is allowed to contend, which means that it tries to send at this time slot. Once I send successfully, okay, then the access point will label this time slot as, okay, node A. That's it. So node A will keep sending on this time slot until it has no further data to send. Then it does not send. When it does not send, the access point will put this time slot in the pool of available time slots. So at the end of every frame, the access point has to tell everyone if this time slot is booked, is reserved for any node, or it's available. Then the nodes will know if it's booked for a certain node, it should never send on this time slot. Only it contends on the time slots that are available. So these time slots, at these time slots, we perform slotted Aloha. Okay, which means that we contend on this time slot. So there is a probability of collision in the data phase.
The A, B, C, D are nodes, no?
Are nodes, yes. Okay, so here in this example, we have frame one. Frame one is like, it's a frame is, in here, a frame is divided into 8 time slots. Could be 10, could be whatever. I specify that. So in frame one, node A, C, D, A, B, A, and F are assigned these time slots. Which means that, as you can see here, node A, from frame 1 all the way to node 5, node A has data to send. Right? Yeah. So node A has data to send at all these time slots. So as long as node A has data to send, خلاص, it can send. Here node C has given away its time slot at frame 3. When node C stops sending, then the access point will declare this as available time slot. It will put it in the available pool of available time slots. Okay, that's it. So the nodes will contend at these time slots. So the advantage here is that I don't have an explicit reservation phase. So I don't have an explicit reservation phase. So here it's implicit reservation. Implicit here coming from the fact that once I send successfully, I seized access to this time slot until I release it.
So in case the third time slot, C sends only for only in 2 frames.
Right.
So in the third frame, C is having that.
C does not have any more data.
Okay.
So خلاص, that's it. So in that case, this time slot will go back to the available pool of time slots.
It can be allotted to further D or C, D or B.
But based on slotted Aloha, so all the nodes will contend on this time slots as long as it's available. Remember, so the available time slots, they are left to any node to access it, which means that 2 nodes may try to access this time slot at any point in time, in which case collision may happen, like here. Here there is collision. Here there is collision. So here there was a collision, and here there was a collision. Why? Because these slots have become available, and 2 nodes tried to send at these time slots, so collision will happen. Okay? So on one hand, this is good because I have actually eliminated the reservation phase. On the other hand, I allowed the collision to happen at the transmission phase. But I tried to reduce that a little bit using the implicit reservation. The difference between this one and normal Aloha is what? Here we have implicit reservation. Through what? If I send successfully on this time slot,
Then it's
I have
from
it.
me.
Then it's like I grabbed it. I can use it from now on until I release it. So this type of reservation increases the efficiency. Okay? Increases the efficiency. But I did not eliminate the collision, because there may happen that I have an available time slot which is not reserved implicitly for any node, and two nodes try to send at this time slot and they will collide.
Suppose, Doctor, one node succeeds in getting that slot, that
Yes.
empty time slot, then
Right.
it will be of that node's performance.
This is what
like
happened here in frame 3, the same time slot which happened to collide here. Here, it's because it's collide. Then here it's become available again, because nobody was successful in seizing this time slot. Then it has become available again. So the node, the access point, will send the fact that this time slot has become available, right? And here node F, see, node F was able to access this successfully. Once node F accesses this successfully, so here node F. Okay, so node F will keep sending until it has no further data to send. So as you can see here, once a node seizes the time slot B, okay? So C and C, okay? A all the time. D all the time. F all the time. So this is an implicit reservation which tends to increase the efficiency, okay, compared to the normal slotted Aloha. So here the third type of reservation is what we call Reservation Tdma. Here, Reservation Tdma, every frame consists of n many slots, okay? In each of these many slots, again, nodes will contend on these time slots, all right? In that case, which is what we have talked about before, each node will not send, in that case, the random number, will send the number of needed time slots that it needs. And each node can request up to k slots, okay? Which means that if I have n nodes, okay, the maximum number of time slots is n times k, which refers to the full load. So at full load, I could have up to n nodes. Each node is requesting k different time slots. So I have all the n times k time slots all taken. Okay? Type. But this is the worst case. What if a node wants only one time slot or two time slots? In which case, I could end again. When a node sends in the reservation phase here, it sends the number of time slots that it needs. But then I need an access point here. I need an access point to tell everyone which time slots is allocated to it. Okay? Because these time slots may be consecutive or maybe not consecutive. I don't know. So in which case, the access point needs to inform everyone which time slots is allocated to it. So maybe one of the nodes or two of the nodes will request one time slot, two time slots, right? Which means that some of these time slots may be empty or idle, right? If I happen to have n times k. Okay? So in that case, I used explicit reservation here, right?
Okay,
I use explicit reservation because I have an explicit reservation phase. Okay? And in this reservation phase and during transmission, I have no collision whatsoever. Similar to the explicit reservation 1, which is the first technique we talked about. In other words, I have to have a phase where there might be some collision, either in the explicit reservation phase, or if I don't have explicit reservation phase, then it will happen in the transmission phase, right? But in any case, I'm trying to increase the efficiency by having any type of reservation, any kind of reservation. So here we talked about 3 different types. In the third type here, as we said, there are some time slots which may end to be idle due to the fact that the requests from these nodes, from the end nodes, they requested less than k time slots. In which case, these time slots, I may actually leave them idle, or I may allocate to other nodes other than the end nodes, other nodes based on best effort, based on round robin. Like these nodes, these time slots, I happen to have 3 time slots, okay? So I have n nodes. These n nodes will encounter no collision whatsoever. And I can provide some quality of service to these nodes based on their requests. When I accommodate all the requests, okay, I have another set of nodes which are called like best effort nodes. Best effort, I can serve these nodes only when I have time. It's like you are going in a bank, okay, and there are certain queues which the queue tells you exactly how many people in front of you and when is your time slot, and you have to wait for this period of time until you get to your time slot, and your turn is deterministic, and you know that beforehand everything is calculated and you know exactly when you will finish, okay? But there are another queue of poor people, very poor people. There is another queue. This queue will almost never be served unless
We do have time.
unless we have time. Okay? So all the other queues will be served with explicit and deterministic service time. Okay? If I do not have any people to serve, then I can get one from the poor people. It's like similar to what happens now in the airport. Like there is like you find like some 10 different stations for people from GCC countries.
Yes, and
Okay.
usually it's not used.
It's not used,
So we.
right? So these people, they have the best service ever, right? And then some of these people, some of these stations, they might become idle at certain point because they don't have anyone to send or anyone to serve. In which case you find the guy is telling you, come from this line and go to here.
Right.
So this is best effort. You don't know when this will happen. So you do not have any expectation when this will happen. It's random. So this is what we call a best effort. So we leave these time slots for best effort, only for best effort. There's no guarantee. But these nodes, they will get some service guarantees. They get some service guarantees. They request, and then they get close to what they request. So they have some idea what will happen. They have some idea how many slots they will get, and there is no contention on these time slots. So they can expect and estimate the amount of time they need to send their transmission. Okay?
And this allows only k time slots to each node. That means if
Maximum k time slots. Maximum k time
So
slots.
it can allot k to one and k minus 1 to another and k minus 3 to another, like that?
Not k plus 1, no. K minus 1, yes. So here, in the reservation Tdma, each node is allowed to request maximum of k time slots. Maximum k time slots, which means that it could be less than k. Could be less than k. And you're right, I could do another mechanism where I don't have to specify k. So based on the requests coming from the nodes, I can allow maybe at some point one node will take all the n plus n times k time slots. أنا حر. and I can give them all to one node or two nodes or three nodes. I have complete freedom. But here, the mechanism, which is, I think this is used by one of the types of wireless networks. I can't remember what that is. That's what they do. So they divide these time slots into n times k, where k is the maximum number of time slots that can be requested by one single node. Maximum. So it could be k minus 1, k minus 2, k minus 3, could be 1, 2, 3, whatever.
So if I request 2 time slots, then how will one will become free and how can it be allotted? Because I already need 2, so I requested 2 to access point and I got 2. Then how will that will be free for getting into the other pool?
Well, if k is 3 in that case, then you requested 2 and you got 2.
Okay.
But the system itself, the system as a whole, uses k equal 3, in which case that there is one of the 3 time slots you do not need at this point in time. Okay? So the system knows that this one now is available. So the system will say, okay, so let's grab one from the best effort nodes and give them this time slot.
It allows only in k time slots. Even if I request 2, maybe k is equal to 3.
Yes.
And I request 2, it
Yes.
allows 3 to me.
No, it allows 2
And
to
one,
you,
one
and one it becomes free for any of the best effort nodes. Okay, so the whole system, you can think of it as like there are 2 queues. One queue has all the people who are using that protocol, using that mechanism, and another queue which is the best effort queue. So this best effort queue, I can serve one of this queue only whenever I have any time slots that are available. Okay, but in normal situation, I'm only serving the queue from the A. I'm only serving nodes in the queue with high probability or high priority. And these nodes, they are served by dividing this into 2 phases. One is the reservation phase, and one is the transmission phase. In the reservation phase, we're using slotted Aloha, and then they send the request. The request is not based on random number. The request here is based on how many time slots each node needs. Based on that, I know how many time slots will be taking and how many time slots will be available. The available ones I can use for best effort, or I can make them idle, whatever I want. Okay. So these are the 3 types of reservation. So another way of increasing the efficiency. So we talked about reservation as a way of increasing the efficiency. Another way of increasing the efficiency is by trying to avoid the collision. Okay. So again, we're not eliminating the collision, but we will try to avoid it as much as we can. And one of these techniques is what we are familiar with, which is MACA, or multiple access with collision avoidance, which uses short signaling packets for collision avoidance. So we have 2 control signals. One is called request to send, and another one is called clear to send. Okay, so maybe you are familiar, Abir, with this RTS CTS one.
I can't remember this stuff.
Okay, so basically, what happens is that we know that when we find the medium idle, okay, we sense first. We see whether somebody is sending on the channel or not. If the channel is idle, then what happens is that we wait for a small period of time, which is called DIFS. In this DIFS, we try to make sure that there is absolutely no transmission on the channel. It's like another way of trying to avoid, because as we said, if 2 nodes try to sense, okay, and then at some point they find that the channel is idle and they try to send immediately, they will collide. But if they wait for a little bit, okay, then there is a chance that one of them will try to send that before the other, okay, in which case the collision will be avoided. Type. But there is a chance that they will also
both
send at the same time. So what will happen? So in order to try to avoid the channel as a third level of trying to avoid the collision, is that when a node finds that the medium is absolutely idle, it sends an announcement which is called request to send. This announcement, it informs
all the nodes.
as many nodes as possible, which is the nodes that are in the transmission range of this node. Okay? To inform them that I'm trying to send data to node X. And this data has this duration of time, and I'm trying to send it to node X. Okay? Why is this? Remember that RTS here is a very short signal. Okay? Why? Because here, if I start transmitting data without informing anyone, maybe another node will sense the channel that it's idle and then it tries to send. Remember that the data duration itself is very long. So the collision may happen at any point in time because the data is long. If the collision happens at 1 nanosecond overlap, then all the data is gone. Yani if I try to send data, this is data, right? This is data. So node 1 is trying to send data. Node 2, if it tries to send here, okay, then there is a small overlap. Both of them lost the data, and the data is very long. Okay? But if this node sends RTS first, okay, so this node will send a very short RTS. The RTS is very short. If this node listens to this RTS, so it knows that node 1 is trying to send. So it will abstain from doing anything. And that's what we're trying to do. Okay?
So this RTS is sent to the receiver, no?
all
No.
nodes
It's broadcast. It's broadcast to everyone. Remember, we're talking about wireless. All signals are broadcast. So RTS is an announcement on the channel. I want to send. And I want to send to node X. So you also specify, and I will tell you why we specify the destination in the RTS now. Okay? So we're informing everyone that we will try to send. Okay. So who will listen to RTS? Well, all nodes in the transmission range of this node. Right? Does this include 100% of the nodes? Not necessarily. Remember the hidden terminal problem?
Yeah.
Remember hidden terminal problem?
All overlap.
So all the nodes that are hidden from me, they will not listen to RTS. They don't know. Okay, so what is the importance of RTS? Well, all the nodes in the transmission range, they will send RTS. I specify the destination because I want the destination to send me clear TS. Okay?
Clear TS means like
Clear,
send me.
clear to send. Clear to send, which means that
I will receive.
I listen to your RTS and I can receive it, and I'm ready to receive it.
Okay.
Right? So the receiver will send clear TS. What will happen to all the other nodes who listen to RTS? They know that the transmitter is trying to send to the receiving nodes, and they should not be part of it, so they go into a phase which is called NAV, or network allocation vector. NAV is like okay, I listen to RTS, I know that node X wants to send to node Y, and I'm not part of it. So,
And no Y accept that.
and
So after the acceptance,
no,
right?
no, they know that node X is trying to send to node Y. Okay. So now they may select to go into nav, which means that okay, I'm not part of it. I'm not node X. I'm not node Y. Okay. Although I have data to send, but somebody else has requested to send before me, so I obey that. So I will not interfere. Okay. So I will go into nav. So only node X and node Y will be in the picture. However, remember, not 100% of the nodes may listen to RTS, right? So when the receiver node sends CTS, which is clear to send, okay, more nodes will listen to CTS. We'll see now. So more nodes will listen to CTS that may not have heard RTS, and we'll see how this will happen. Okay, so the nodes that will listen to CTS, they will go also into nav. That's why there is nav RTS, nav CTS, okay? And that may not include 100% of it. And that's why all this procedure is trying to avoid the collision, but it never actually eliminates the collision completely. Okay? Only reservation eliminates, and as we have seen, only in parts of the time, not 100% of the time. Okay? So then and only then, if the transmitter receives clear to send, then it sends the data. So now I can send it, which means that in order to send one data transmission, we have to send RTS, receive CTS, send data, and receive acknowledgement. Why acknowledgement? Because this is our only way of figuring out whether there was a collision or any transmission error, right? Because again, remember, we cannot detect the collision. We did not eliminate it. With all these precautions, we did not eliminate it, and we know that. We did not eliminate it, right? And we cannot detect it. So what is the only way to realize that there may have been a collision or there may have been any transmission error? Is not by receiving the acknowledgement. Is by receiving no acknowledgement, I mean. If I don't receive acknowledgement, then I realize that there was an error. Whether this error is 90% of the time is collision, but there may be some other chances that there may be some transmission error. All right, so send data and wait for acknowledgement. So some nodes, they may not listen to RTS, but they may have listened to CTS. Some nodes may not have listened to CTS, in which case they may be listen to data. Some nodes may never have received any of them, which means that it may try to send a collision will happen. You never know. Okay? In which case, if there is any type of collision, then acknowledgement.
That is also broadcast. So how come the other nodes know that whether it is data or RTS or CTS? Yes.
So remember, in the MAC layer, all nodes, they may actually receive, or at least good percentage of the nodes, they will receive the frame. They will read what's in this frame. Okay? So when they read RTS, they actually read the frame. Okay? They know that this RTS is not for them. So they will not process it any further. They will just go into nav and ignore it. Okay? When they receive data, they actually read the data. They know that the destination is not them. Okay? So they know that the destination is not them. If the destination is me, only then I can send it to the upper layers, to the network layer, because this is data. It's meant to me. So I can send it to the upper layer to complete the reception of this in the network layer and so on. Okay? But if I'm not the destination, then I just ignore it. I delete it. That's it. Okay? So this is the overhead in wireless. That's why wireless has huge amount of overhead, because all the nodes listen to most of the frames, even if this frame is not distant to them. And that's why wireless is very tricky, because it consumes energy all the time, because all the time I'm receiving some frames and I have to process these frames. with these frames, it's RTS, CTS, acknowledgement, data. So I keep processing frames all the time. Okay? So that's how we use RTS. So here, this very quickly shows us how Mecca using RTS and CTS avoids the hidden terminal problem and exposed terminal problem. Remember, when A sends to B, C is hidden, so C will try to send to B and the collision will happen at B, right? So this happens if we send the data transmission, and we remember that data transmission is huge, is the duration is very, so C will have to wait for like 100 milliseconds, not trying to do anything, okay, in order for this in order for having no collision at B. When we use RTS CTS, what will happen is that when we send RTS to B,
B will send CTS to
B
all
will send
the
CTS. So C will listen to CTS. It will not listen to RTS. So it's still hidden from RTS, but it will listen to CTS.
So
And because these, again, remember, these signals are very, very short. So hopefully this RTS CTS will happen before C tries to do anything. But the problem with data is that data is very huge. So there is a high probability that C, because it does not listen to this data, it does not know that A is sending to B. And for a very long duration of time, for like 200 milliseconds, so there is a chance that C will try to send them and collision will happen. But this RTS CTS avoids that. Again here, when A tries to send to B, here C is trying to send to another node D. So, here in the exposed terminal problem, B is trying to send to A. So C will know that from the RTS that B is trying to send to A. And C wants to send to D, which is another node, right? So it knows that its own transmission is not relevant to this transmission.
So it will send
Because RTS here will tell node C that B is trying to send to A. Since C is trying to send to another node, then C may in fact move forward with that. Given that when C tries to send RTS to D, this RTS will not collide with this RTS. Right. So that's the only condition. But because these signals are very short, the collision in RTS is very low probability. In which case, a scenario like the exposed terminal problem may be avoided very easily. Okay. So C in that case may move forward with the transmission because it knows that B is trying to send to A, and it does not want to send to A anything. It wants to send to D, and D is different. D is a different destination, so it can move forward with that. All right. Any question? So using this RTS CTS, we can avoid the hidden terminal problem and exposed terminal. Remember, exposed terminal problem was not to avoid collision. Exposed terminal problem, we explained it last time, that C is trying to send to D, and it will not send to D because it will listen to the transmission from B, and it will listen to the data. So it will not send to D because B is trying to send. But now when it was informed by RTS that B is sending to A and it has nothing to do with that, then C may in fact move forward with the transmission to D, which means that C will not lose the opportunity of transmitting to D.
But here RTS is being sent both to A and C simultaneously.
Yeah, because B is
right,
sending.
because B is sending. RTS here is a broadcast.
Yeah.
So it will listen. It will be listened to by both A and C.
But C, on hearing RTS from B, it should give a priority to B, no? because it has received a request on B.
Right, but it knows in RTS. In RTS, there is the destination. The destination it includes the destination, which in that case is A. So it's up to C now whether to perform nav and sleep and not engage in any transmission, or it may actually say, well, if I send to D, what does this have to do anything with B transmitting to A? It doesn't. Then in that case, C may say, okay, I will move forward with that. Okay? And this is in fact what happens in the standards. If I know that RTS does not include, so RTS nav RTS is actually conditional. So nav RTS is somewhat conditional. So it's not, nav RTS is not always that I will stay idle. And that's why there is a difference between nav RTS, nav CTS, nav data. Yes, each one of them has a different procedure. Okay, so
means NAV. What's the full form for that?
So there is in the previous slide. I don't want to go back. In the previous slide, we talked about nav RTS, nav CTS, and nav data. Right?
That's on the full form. And
what is the abbreviation of?
Abbreviation. NAV means full.
Oh, network address vector.
Network address.
Yes, network address vector. I don't know why they call it network address vector. The name is not descriptive of what it needs to do, because what needs to be done in that case is that you need to refrain from engaging into this transmission or interfering with this transmission. But in the exposed terminal problem, we know that we will not interfere with this transmission because C wants to send to another node which has nothing to do with A.
It's completely different sets.
It's a completely different transmission.
And what is SIFS and DIFS?
Oh, right, that's a good question. So SIFS is a short interframe spacing. DIFS is DCF interframe spacing. So, yeah, as we said, DIFS is a period of time that we wait to make sure that the channel is absolutely idle during a certain period of time. And that's a second level of trying to avoid the collision.
And that's happened only once?
Only once at the beginning of each frame.
Right.
Of each frame. Okay? SIFS has a different purpose. SIFS is always needed when you switch from reception to transmission or from transmission to reception. So that's why I try to do it from RTS to CTS. Remember, because RTS is transmission, right? And CTS is the reception, or the other way around. So the receiver will receive RTS and will send CTS. So it will have to switch from reception to transmission. So usually when you do this, you need SIFS. Why? Because you need to switch your hardware from reception to transmission. Usually this SIFS is extremely short. That's why they call it short interframe spacing. It's extremely short. And it's only needed to calibrate the hardware from reception to transmission. So it has different purpose altogether from DIFS. DIFS has a different purpose. Okay?
But I did not get the concept of DIFS. SIFS I understood. But
DIFS, if I sense the channel and the channel is idle, okay? Then if I try to send data, what will happen is that data will be a long duration of time. So if a node tries to sense right after I try to transmit, maybe it will find that the channel is idle, right? So it may actually try to send, and in that case we will collide, right? So in order for me to make sure that the channel is idle is when I actually wait for a certain period of time and then sense again. If I sense here and it's idle, and if I waited until DIFS and then I sense again, and then the node is, and then the channel is also idle, this means that for sure the channel is completely idle.
Duration interference spacing.
Yes. It's not duration. It stands for DCF. DCF is the it's called the distributed coordination function, which is actually this RTS CTS thing. So we'll talk about this next time, inshallah.